Yeah.
Okay, so like Aisha was saying, this is my book from last year, Waves with Power Law Attenuation, and I want to present some aspects of it, and with a focus on trying to sort of address rock physics to the degree that I address that. And I just want to move something here. Like this. Is it still okay, or did I put something in front of the screen now?
There's something in front of the screen.
Okay.
Yeah,
So
no, it's okay.
Yeah. So I move it there. Okay. So just to put this in context, I'd like to just show this. This is supposedly an illustration of an electron, and we are not working with the very small, neither are we working with the very large, with the galaxies and stuff. But there is a British cosmologist and astrophysicist, Martin Reeves, who says that black holes are simpler than forests, and science has its limits. And I'm talking about how we can expect big advances in the very small and the very large, but also in the very complex. And this is what I mean by the very complex. This is the fractal structure of the blood vessels in a kidney. And this is an ultrasound image of a kidney, not the same kidney, but for illustration. And so, like Aisha was saying in the introduction, my sort of quest is to understand how these fractals and other properties of the media impact on these images. And my book on this has two parts. One is on acoustics and linear viscoelasticity with classical acoustics and also classical viscoelasticity, because these topics are not very often coupled, but they are actually quite similar, acoustics and viscoelasticity. And then in part two is the sort of the main topic, the power law media, with chapter 5 from constitutive equations and chapter 6 from phenomenological wave equations. And I'm going to cover those very briefly, or say a little bit about them, and also something about chapter 7 and how we can justify that. Some examples from chapter 8 on porous media, because that's relevant for rock physics, and also from chapter 9 on fractal scattering media. And my sort of outline is really this, that you can find power law attenuation everywhere, and then I'm going to illustrate it from the BO model, so that's in the porous media, and something more on what this fractional derivative really is, how we can justify these power law models, and some wave equations based on fractional models, and finally the scattering in fractals. To start this very sort of basic, this is how we derive a wave equation. Start with some conservation laws, which is usually conservation of mass and conservation of momentum to the upper left, and then we need some description of the material. And the very simplest description you can have is a spring. And so this illustration is for my sort of teenage hero, which is quite some years ago, but a guitar string can be modeled as a first approximation as a spring. And when you combine this, you get this lossless wave equation with a second order derivative in space and one in time, and the speed of sound, which is given by the elasticity of the spring and the density of the medium. Let's see if I can turn on the pointer here, like this. Does the pointer work now? Yeah. And in order to analyze such a wave equation, starting with the wave equation up here, we assume a plane wave solution in space and time, and we get a dispersion relation. And in this simple case, the wave number is just proportional to frequency. And the wave number can be analyzed then for the real part for the phase velocity and the imaginary part for the attenuation, and that's what I'm going to do. And when I talk about the waves with power law attenuation, this is what I mean. I mean, we have a sinusoidal wave, but damped. And all of these four examples are very heavily damped, actually. And it's damped more and more here, and eventually this is the solution of a diffusion equation. So it's damped to the so much that the sinusoid is more or less gone. And with power law, I mean that the damping term follows a power law with frequency. And I think many of you will be familiar with that from rock physics, where Y often is sort of close to 1. And that's the case for medical ultrasound as well. And it can be characterized in dBs per meter, loss per wavelength, also in terms of inverse Q. And if Y equal 1 here, inverse Q is usually constant. Okay. Is there a possibility for people to interrupt and ask questions here?
I think we will keep at the end.
Okay. But I just need confirmation that you're hearing me. So
Yeah. I just, I muted people, so we can.
That's good. So please call me on the mobile phone if something falls out.
We have also possibility that they can write their questions at the end in the chat box.
Okay, very good. Yeah, so that's the introduction. Then my first point, power law attenuation is everywhere. So I like to show this graph. It's a graph covering from 1 megahertz and down to 10 kilohertz. 10 kilohertz, 1 megahertz, 100 megahertz, 1 gigahertz. And you have granite, even both for longitudinal waves and shear waves, which has a power law close to 1. There's another kind of granite for higher frequencies. And also for liver, so in biological tissue, this example is Y equal 1.3, but it can vary from 1 to 1.5 or something like that. And this YIG material with a power law exponent of 2. So in that range from 1 to 2 is quite typical. What one should note from here is that it's rare actually to have measurements over, in this case, like 1 decade. And here's for 2 decades, which is quite rare actually. And so when I come to fractional wave equations, they cover all frequencies. So that's just one way to model this. There are other ways, which I'll also discuss to some extent, which will only cover the range of the measurements. So the fractional ones will cover all frequencies. So they model more than we have data for. Now, just to take some reference material, some simple ones, which are very well understood. This is the absorption in seawater, and here I'm from, let me see, from 1 kilohertz, 1 megahertz, 10 megahertz. And attenuation is in dB per kilometer. And the distilled water attenuation is a viscous process. It just follows frequency to the power 2. And then there is a relaxation process due to boric acid, and another one at frequencies around 1 kilohertz, and another one due to magnesium sulfate, so in the tens or maybe 100 kilohertz. And I've plotted here just for fun, more or less, but some typical parameters: temperature, salinity, pH, and depth. For the Baltic Sea down here, for the Arctic Sea is the blue, it looks ice cold. The Red Sea is red, and the Pacific the green. So there is some variation depending on salinity in particular. Now, this is very well understood. We understand it down to the molecular level, and we can predict how these relaxation processes behave as a function of these material parameters. Unfortunately, that's not the case for more complex materials. And so when I make a comparison now, I'll take out 1 to 10 megahertz and compare it to tissue and ultrasound. So my axis is now from 1 to 10 megahertz. And now I'm at dB per centimeters because kilometers is no longer relevant. And so water, then I've taken out the Arctic and the distilled because those are the two extremes at these high frequencies. And the black curve here is the typical model assumed for tissue, which is half a dB per centimeter and attenuation that rises with proportional to frequency. There is quite some variation between tissues, but what you see is that the power law exponent is closer to 1 than 2, which is the case for water. Now the interesting thing for tissue is that all it takes, first, the attenuation is also substantially higher. So 2.5 dB per centimeter at 5 megahertz for tissue, and salt water 2.1 dB per centimeter. Interestingly, for tissue, all you need is really milk. Just the proteins in milk will give you the same attenuation as tissue. So there are some polymer chains or something like that which causes the major part of the attenuation. So that's one of the applications I'm coming from. The other one is this elastography, which is remote palpation using an external vibrator, and you can vibrate like here. It's myself actually in a MR scanner in Zurich, vibrating the brain, and you can use MR or ultrasound like here to record data. And this is just an example. Standard ultrasound to the left, which hardly sees this inclusion, and a 50 hertz share wave. You see the wave pattern, and then you see the inclusion more or less not defined in the share wave image. So that's one. That's the second application. The third one is in underwater acoustics, sound propagation in water over a sediment. So here is the bottom, and so this down here is the sediment, and this is the water. And when you have low frequencies like the hundreds of hertz, and you want a real long wave propagation, then the reflection coefficient and the mode conversion and the modes that propagate in the bottom will actually influence what goes on in the water as well. And in order to predict it, the long range properties like tens or hundreds of kilometers, you need to take that into account. This is a 400 hertz example. But then we need this biotheory for poroelastic media composed of solids and fluids, or a viscous grain sharing theory, which is the alternative. And this is, I guess, closer to Schlumberger than the ultrasound image. So the equation which is known is an equation like this, a viscous wave equation, the Stokes equation, which is based on what's called the Kelvin-Voigt model in linear viscoelasticity, a spring for the elasticity and a damper for the viscosity. So it's a simple model for a car suspension system, if you like, or any viscoelastic medium. And what happens is that you get an additional loss term in the wave equation. And you can describe a damped wave. And it doesn't matter whether you, like I'm assuming here, and take this from the Kelvin-Voigt model, or I can do this via the Navier-Stokes equation, which is, if I remember right, a modification of the, or additional terms in the momentum balance of Euler's equation. But what's been well known since 1845 is that you get quadratic equations. So the simplest model for the model for the distilled water can be described in this case. But my sort of question when I started in this, and like Aisha was saying, was also working with Aisha at that time. We also had a collaborator, Wen Chen, who later became a professor at Huai University in China, in Nanjing. Unfortunately, he died 1.5 years ago. But is there a wave equation for arbitrary power law, not just quadratic, and also other constitutive equations, material equations for arbitrary power laws? And we did some nice work in trying to exploit that, and actually there is an equation up here. This was a conference in 2012 in Nanjing, where this equation was the it wasn't all the promotional material for the conference, and it's with a fractional equation, and it's people sometimes call it the Sverre Holm equation now, and so it's my little moment of fame, I guess, for Wen and me. But this equation and other equations can be found by just fixing the loss operator, and this is my chapter in my book on these ad hoc equations. So we can start with the viscous equation. The tau now is the ratio of viscosity and elasticity. And one modification of it, often used in acoustics, is to replace the fractional Laplacian by a temporal derivative. And to some approximation, these are the same. And then we can fix it. We can get fractional derivative loss terms by just generalizing the third order derivatives, and now make it alpha plus 2. So now we have a fractional order derivative instead, and the scaling factor given. I won't go into what these are, but these are constants given by the properties. So that's one way to sort of fix it. Another way is to do the same, something similar with the fractional, with the Laplacian, and replace it by a fractional Laplacian. And then obviously there is a third way we can fix. We can do something about the temporal derivative here. That fractional. That goes back to Caputo in 1967 and others. Now I've put this in green because this wave equation is different because it can actually be derived from a constitutive law, and that's not the case for the two red ones here. So it is better in some way. Now, but I've just threw in a fractional derivative here, both in time and in space. I'm going to concentrate on time from now on, but what do I mean? What is it? And I'm assuming that all of you are familiar with Fourier transforms. So here's I go to the Fourier domain by integrating with this exponential kernel, and I can go back with the complex conjugate kernel. And then the Fourier transform property of a derivative is just if it's an integer derivative to the power n, it's just I omega to the power n. So first order derivative, you multiply by I omega. Second order, you multiply by I omega to the power 2. And so it's straightforward to generalize that and just let that n be alpha. And so a half order derivative has a Fourier transform which scales the Fourier transform of the function by I omega to the power half, or the square root of I omega, for instance. So this is actually the more or less the only definition of a fractional derivative that I need in my book, because I'm mostly working with dispersion relations, and then they're always in the Fourier domain. But let's see how this applies to something a little bit more physical than the old ad hoc modification I did. So point 2 here is the turbulence in the Biot model. And the Biot model, I think that many of you, or maybe all of you, are familiar to some aspects of that. Here I'm illustrating it for bone, but a rock is quite similar. So there is some solid, and then there is pores with there is a skeleton, the dark one, and then there is a fluid in between. And there is a pressure on it also, just like in a sediment. And then it's well known from the 50s that which Biot derived that you get 2 compressional waves and 1 shear wave. And the slow compressional wave is heavily damped because then motion in the solid and the fluid are out of phase with each other. And you can characterize this by a large set of parameters, porosities, densities in the two phases, and bulk model the two phases, viscosity, permeability, pores, pore sizes, the straightness of the pores, tortuosity, and also characterize the rigid frame. And I have examples with sediments and with brain tissue. Now, the shear wave is particularly interesting for elastography, so that's why I've sort of concentrated a little bit on that. But the shear wave solution is a solution to the matrix equation like this. And there, so the one solution comes out of here. There is a second solution, which is omega equals 0, which is a non-propagating solution as well, actually. But in the case, there is an F here, which in case of laminar flow in the pores is just a constant. But if there is turbulence, then that F is replaced by what's called a viscodynamic operator, which is given by some Bessel functions. And I won't go into the details here, but the argument in that in those Bessel functions is given by the pore radius in the Biot model, the R here and the wave number. And then there is a scaling by densities and viscosity. And it turns out that this complicated Bessel function expression is fairly well approximated by the square root of I omega tau. And then maybe you start seeing my connection to the fractional derivatives. And Biot showed this, and he also showed that if you assume a square pore rather than a round pore with a radius, you can approximate it with the same square root of I omega and a constant. So since we don't really know the shape of the pore, whether it's round or square or something in between or elliptical or whatever, it's too detailed to really model it with the Bessel functions, but this sort of common approximation is more appropriate. And what this turbulence term does is that when you look at, I'm plotting in terms of attenuation in dBs per meter squared, so not inverse Q, which is maybe more common in your field, but as a function of frequency in white matter in brain. So now I'm at from 1 Hertz to 100 Hertz to 10,000 Hertz megahertz. The turbulence term plays a role when you come to high frequencies. Then it will lift the attenuation and be proportional to square root of frequency, actually. And you can see that 10 to the power 4 you would never have. The attenuation is so big here, it's like many thousands of dBs per meter, so there's actually no propagation. So if we were to image a brain with shear waves, which we do, we are down here at like 100 Hertz. So the turbulence term doesn't really play a role, but in the model, of course, we can model it. The phase velocity, in this case 0.3 to 0.35 meters per second, is not very much influenced by the turbulence term. Human tissue is very special in the way that there is a very big contrast between the phase velocities of the compressional wave and the shear wave. So compressional wave 1500 meters per second, compressional wave 0.3 is very slow here, but 1 to 2 meters per second is maybe more typical. But there is a large difference between them because the Poisson ratio is very, very close to 0.5. I think in rocks it's more, or sediments, it's more like maybe 2000, or at least very with quite a lot of fluid in them, like the phase velocity would be 2000 meters per second and the shear velocity may be 100 or 200 meters per second. So the contrast between the two wave modes is not as big as in human tissue. But if I go back here, this square root of I omega tau and my Fourier property sort of hints at the time domain operator corresponding to this is approximately a half order derivative. And so you can actually go back to the Biot theory, with turbulence, and you can find the wave equation by using these kinds of approximations and substitutions and this operator. And you end up with a wave equation like this, which looks terrible, but which I think is actually quite beautiful. The first terms are the lossless terms. Then there is a term with a second order Laplacian and a half order derivative. So it reminds you of the viscous wave equation, where you have a full first order derivative, but now we have a half order derivative. And then there is an additional term with 2.5 order derivative. And this actually corresponds to a half order fractional Zeno model, which I haven't introduced that, but it's the standard linear solid with 2 springs and a damper, and where the damper has become fractional. So it's a standard model, decimal pointer. So this quite involved way of doing this via Biot model and the turbulence and the half order derivative gives us what looks like a messy model, but which is actually a standard fractional model. In the sediment case, Biot shares solution with turbulence in the sediment case. Then I can approximate it with so that's the black one here. Now I'm from 100 hertz, 1 kilohertz, 10,000 hertz, 100,000 hertz. The Biot model is the black one, the attenuation, and the phase velocity is here. And I can approximate the equation I had in the previous slide has an attenuation which follows the red one. So as we come to hundreds of kilohertz, is a good approximation to the more involved Biot model. And it's just a standard linear solid model, the Zeno model, will approximate the low frequencies. And it's similar for the phase velocity. So now I'm at 100 meters per second phase velocities, which is, I think, more realistic for share waves in a sediment. Okay, so I've thrown in some half-order derivatives and a 2.5 order derivative. 2.5 order derivative, by the way, is just a second order derivative and then a half order derivative. So it's both of them are half order derivatives in a sense. Now, what is this fractional derivative? And we go a little bit into what it is, not just in the frequency domain. And the first physical problem which was posed, which ended up with a fractional model, was called Abel's mechanical problem. And Niels Henrik Abel was a Norwegian mathematician who died from 1802, 1829, died very young. I think he was only 26 actually when he died. And this curve that I'm illustrating is called the tautochrone or isochrone curve. It has a shape which is such that whether you drop the blue ball from up here or the yellow ball from down here, they use exactly the same time to reach the bottom. So the shape is designed to give a time of descent which is independent of height. Now he generalized it, so now he wants to see, okay, if I don't have that time as a function of height as a constant, but if he just wanted to find the time to descent as a function of the height and the curve shape. Then he found that it's quite simple. It's just an energy balance between kinetic energy and potential energy. And then you can find that the time for descent is given as 1 over the square root of a, the height minus this variable x, times the derivative of the curve shape. And this turns out to be what's called the Caputo derivative of a half order. So that's why it's called the first physical problem with the fractional derivative. And Abel also inverts it, so he finds the s as a function of the time, and that's a half order fractional integral, or the minus half order derivative. I thought until just recently that he did this in 1826, at the age of 24, because that can be found in his complete works from 1839. But I just discovered that, or I was actually made aware of a paper that shows that this is actually in one of his very early papers, 1823, and not just does he show that this is a half-order derivative, but he actually gives the whole theory for fractional derivatives. Now this is in Norwegian because, and hopefully at least some of you may understand the text of it, at least you understand the equations, because he published it in sort of Norwegian Danish. He says he found the following merkverdig theorem, which is something, the following remarkable theorem. And what he has here is see down here, he has found that the S is the minus n, and n is between 0 and 1 order derivative of the time to descent. And this is the definition of a fractional integral. So this is like the Caputo fractional derivative, or at least it's proportional to it. And the inverse uses the Cauchy formula for repeated integration, and it shows this just for fun. This has a remarkable theorem, and here it says for dens besynderlighetsskyld, so which is like, does it mean in English something like for sake of curiosity? This is what I found. But unfortunately, Abel didn't follow up on this, so this is just in that Norwegian-Danish article from 1823, which wasn't translated into French until the 1880s, so it was sort of unknown for a long time. But this is found, is usually attributed to Louville, the French mathematician in 1832. So he was 9 years ahead of it. So he assumes that these non-integer order derivatives and integrals are inverses of each other, and he assumes the fundamental theorem of calculus for non-integer orders. I had a seminar about this yesterday, actually, in the math department. So we have actually two interpretations now of the fractional derivative. What I showed first, the Fourier transform. And if we take the Fourier transform interpretation and sort of divide it into two components. One is of integer order, I omega to the m, and then a non-integer order, alpha minus m. So if I want to do a half-order integral, I have I omega to the power 1 here, and I omega to the half minus 1, so minus a half. And then you can see that this is a Fourier transform of an ordinary derivative of order n, m in 1 in my case, which is, we know how to invert, and the product of another kernel. And a product in the Fourier domain is a convolution in the temporal domain. So if you neglect this part now and just, so it means that the fractional derivative is a standard derivative due to this I omega to the power m, and a convolution denoted by the star of the inverse Fourier transform of this power law. And the inverse Fourier transform of a power law is another power law. This power law function has this particular property that the power law Fourier transforms into another power law scaled by a gamma function. So that's another way to arrive at or to find what this frequency domain function means, and then you can interpret this in two different ways: the Riemann-Liouville and the Caputo. I won't go into the details here. But the fractional derivative can also be interpreted for some very simple functions. If you take an exponential function, the formula for the derivative can easily be generalized to a fractional derivative. And here I have an example: y equal e to the power to 2x. Its derivative is 2 times that. Its second order derivative 4 times that. And let's see if I can. Start this now. Yeah, this is the fractional derivative. The order is up here. So now I'm at half order derivative, so I'm half between the function itself and the first order derivative. And then I'm increasing now from 1 to first order to 1.5 order derivative, and then eventually the second order derivative. And when I have an exponential, I can do the same thing. I can use a complex factor here, and then I can do the same thing for a sinusoid. And the formula for the derivative of a sinusoid will actually just be a phase shift. Because here I have a sinusoid in the red, and I have a first order derivative in the black, and the second order derivative in the greenish. And then there is 90 degrees and 180 degrees between them. And the fractional derivative will just interpolate continuously between that. So now I'm 45 degrees offset, that's half order derivative, and 90 degrees offset is a first order derivative, and so on. So I get to the second order derivative. So there are some functions like these are very simple to interpret. Okay, a little bit about justification for these power laws. See, I'm using up my time, but so one way to justify it is that you can approximate these power laws by just adding up many models, many elementary models. The Xeno model that I've been talking about is this spring and the dashpot in parallel, standard linear solid. But if we just keep adding springs and dampers and the dynamic modulus, just add sub-contributions, then here's an example where I've tried to model omega to the power 1.3, and I put the time constants of each of these additional springs and dashpots. They are spread evenly in the log frequency domain. And I use a weighting function to approximate omega to the 1.3, and then it's easy to derive what that is, and I have it in the book. But then you can see that now I get a finite frequency range, the blue one here, approximation to omega to the 1.3. So we could, of course, think of a fractional wave equation, since it models all frequencies, as being a model which has like an infinite number of these relaxation processes, and that's the most common way to interpret physically what goes on when you have these power laws. But my question is, why this particular weighting, and why this log spread of relaxation frequencies? Is there some sort of underlying rationale for that? And I have to admit that I haven't really found that. There is something fractal there, I think. But so we can even interpret the extended Biot model, which is used in this sediment acoustics, like in this acoustics of the seabed as a porolastic medium by Nick Shatiras. You can interpret that in terms of these multiple relaxation functions. And you can even interpret it in terms of ladder functions, like spring dashpots in a ladder. This will approximate to a half-order model, like the square root of I omega tau. And this is a very simple polymer model, so it's relevant for mine milk, perhaps. If all the springs and dampers are equal, you get a half-order model, and you can, if you start playing with the springs and the dampers along the ladder, you can get other orders as well. Or you can have a self-similar tree like this, the same spring, the same dashpots in this self-similar tree. This is an exact half-order model, and which also can be generalized by replacing the viscous element by fractal viscous elements and so on. Another way which we have found is we have found that you can also get a fractional model out of time-varying non-Newtonian viscosity. And an example of such a viscosity that you may be familiar with is paint. It's a thixotropic material where when you don't agitate it, it's quite viscous, but when you agitate it, it becomes sort of more fluid, less viscous, because you want it to be easy to smear out, but you want it to sort of be more viscous so that it doesn't drip. A rheopectic material, which is the opposite, is in the process of whipping cream, you start with the cream, which is milk-like, and you whip it and it becomes more viscous. So then the viscosity increases. With the thixotropic, it decreases with time. If I have a time-varying viscosity, and I look at the relaxation modulus, which is the stress response to a unit step in strain, because we cannot do impulse responses in rheology, so we do unit steps instead. Then we have a time-varying system. And it can be shown that if we have such an linearly increasing viscosity, this is a very good approximation of a fractional derivative damper, where the parameters in the two systems are linked to each other. So we had a paper in Physical Review E some years ago with a PhD student about this. So they're equivalent, and the parameters, the order, for instance, is given by the spring constant and the time varying factor in the viscosity. If we do the opposite response, the creep compliance, which is not the stress response to a step in strain, but a strain response to a unit step in stress, then the same system, time-varying system, will actually have a creep compliance, which is what is known as Lomnitz's law, which is an empirical law for first proposed in 1956 for igneous rocks, like this from volcanic eruptions, and this creep law is also used for wood, where example is spruce wood, and where logarithmic models have been introduced by King or in the 60s. And this paper from 2019 is interesting because they refer to our paper because they sort of claim it has the first physical interpretation of logarithmic creep laws in our Pandy and Holm paper. And so it's kind of interesting. So these kinds of materials also have this, just like igneous rocks. Now, let me give some fractional wave equations. We can take the spring dashpot of the viscous model and of the standard linear solid, and we can replace this the dashpots, the dampers, by fractional dashpots. We had a review paper about that some years ago. This BO example that I had a half-order model there. And then the constitutive law of the simplest model this one, will now have a fractional term instead of a Newtonian viscosity. And this model will have two fractional terms, actually, between stress and stress and strain. And then you go from the standard models have these black relaxation modulus, which is an exponential function, to this dashed function, which is given by this what's called the Mittag-Leffler function. The Mittag-Leffler function is a generalization of the exponential. So this is the power series for an exponential in the case of alpha equal 1, but for other alphas it's different. And here we have a Mittag-Leffler function with a minus quadratic argument, and that particular function has a power law asymptote, and that's what you see here. The tail lasts much longer in the case of a fractional model than in case of the exponential decay of the standard model. And these power law responses, time-domain responses, are found in many biological materials, brain and bone and liver and so on, and also many non-biological materials, metals, glass, rubber, polymers, and so on. So by doing that, by replacing the damper by this fractional damper, you can do this in the viscous model. Now we have a fractional loss operator based on the fractional constitutive law, and this is actually the equation I gave in this ad hoc way with a green circle around it, but now derived from a constitutive law, so that's why it has a little bit more physical significance than the other ones. And you can do the same thing with the slightly more complex model with an additional spring, and you get two terms there. And if you remember the asymptotic wave equation I had for the BO case with BO model, the porous model with turbulence, that's this wave equation with alpha equal half. That's none of the problems of the viscous model with infinite phase velocities and so on. So let me end with my last point, which is very brief, but you can also get power laws independent of these fractional models from scattering in a fractal, and this is actually something I've learned from the seismic field. Because there are two ways you can lose energy in a medium. You can have apparent loss, where energy is only redirected and not converted to heat. So you have energy coming in and then it bounces off to all kinds of directions, and if your sensor is just on the other side, you don't pick it up. So it's lost, but it's not converted to heat, it just takes off in other directions. And in seismics, I think the conventional wisdom is that there's probably a mix of these depending on rock type and frequency. Some of it is due to multiple scattering, some of it is due to conversion to heat and proper viscosity. In elastography and in medical imaging, we believe also that actually maybe more than in rock physics that multiple scattering plays a role, and we try to relate it to cancer tumor growth and how this is under the skin arteriovenous network, normal in the normal case, and here is a tumor case. So the fractality seems to change the tumor or the staging of the tumor. So we try to relate that to power law, coefficients, and so on. And the model here is from this Doherty-Anstin model from European Association of Explorative Geophysics, I think, where you have waves coming in. This is this layered Earth model, but I've rotated it 90 degrees, and you have first multiples, you have second multiples, and you can sum up all the multiples of first order, second order, third order, and so on, based on the reflection coefficients between each layer, and you can find how the transmitted response depends on the Fourier transform of the reflection coefficient series. And Garnier and Selna, whom we are working with, have done this if the reflection coefficients have fractal properties, because then this will end up describing power laws as well. And we had a paper in Physical Review Letters some years ago where we did this for artificially generated fractal media. Where we can sense the fractal microscopic structure via dispersion of the waves. And the waves had much larger wavelength than the fractal geometries. And now we are continuing that in 3D. We are 3D printing fractals, and the size here is just 3 centimeters. We're putting forests of these 3D printed structures, and then we embed them in a as lossless as possible gel, and then we put them into the MR scanner and we try to characterize different fractal dimensions of the printed trees. And now we're back to what I started, where Martin Rees was saying that black holes are simpler than forests, and so to understand what goes on in a forest like this, I like what he's saying, that it's more complex than a black hole. Maybe it's true. I'm hoping it's true. So that's ongoing research. So now I'm wrapping up here. I've talked about the power laws everywhere, talked about the BO model and turbulence, what the fractional derivative is, how we can justify these power law models in terms especially of multiple relaxation and time varying viscosity, some examples of wave equations, and also very brief into how we get power laws from scattering in fractal medias. So what I'm interested in is if these fractional wave equations give clues to some deeper reality, or if they're just a very compact phenomenological description. It's nice math, but is it physics? And if there is a common underlying framework for power laws across applications, is it the same for rocks as for biomedical materials, for instance? Some things indicate that, because this omega to the power 1 kind of variation is very similar in the two very different applications. So, ending with my book and the two parts, conventional and the power law acoustics. So thanks for your patience. I hope you were able to follow me to the very end here.